shout out to all 12 of you for being here so early. Yay! Yeah, I realize it's still early in the morning, but we're going to start off with a very technical talk anyway, so stay awake, hang in there. Anyway, today I'm going to talk about 3 of my favorite things: JavaScript, Unicode, and 90s gangster rap. So you've come to the right place. Anyway, this is me. I'm Mathias. I work for Opera Software in developer relations, and both as part of my job and in my spare time, I like to collaborate on various open source projects. And one example of such a project is Unicode.js, which you see in action here. It's a project I worked on a couple of years ago. And Unicode essentially is the name of an algorithm that converts domain names with special non-ASCII characters in them, like well, an emoji, for example, or like a character with an accent on top of it. It converts it into a pure ASCII form for that same domain name. And the reason Unicode exists is because at the DNS level, domain names can only really contain ASCII characters. So Unicode is essentially a hack that allows you to register domain names containing these special characters, even though at the core level, at the DNS level, those domain names wouldn't otherwise work. So Unicode defines an algorithm that converts back and forth between these 2 representations. Now, anyway, the algorithm is fairly well defined. There is a whole specification dedicated to it, and there is also an example implementation written in C. So when I wanted to write an implementation in JavaScript, I thought, how hard can it be? I just take a look at this specification, maybe take a look at the example code as well, and just port that to JavaScript. It shouldn't really be that hard. But it turns out I was wrong about that, because I learned a lot of new things about how JavaScript handles strings and Unicode specifically while I was working on this library. And that's what I will talk about today. But first, we probably need to talk about this guy. Does anyone know who that is? You can shout. JayZ, of course, everyone knows it's JayZ. He's a famous American rapper, right? But a little known fact about him is that he once decided to write a JavaScript program. But instead, he ended up writing a song about his frustrations with the language. And you may have heard of this song before. It's called 99 Problems. Now, don't get me wrong, I absolutely love JavaScript. In fact, it's my favorite programming language. But just like with any other programming language, I think it's fair to say that if you don't know the entire language and all its weird quirks and details by heart, you're just going to be surprised every now and then. That's just what life as a programmer is like. And that's also the reason why we have websites like phpwhatthefuck.org, which nicely lists all these weird and quirky behaviors in the PHP language. And we have the same thing for JavaScript. It's called whatthefuckjs.com. And there's a lot of weird stuff on there. But of course, everything on these websites can perfectly be explained if you just look at the documentation for PHP, or even the source code for PHP, or for JavaScript if you look up the specification, or, well, the example implementations of JavaScript engines in browsers. So everything can be explained, even the weird parts. But even then, if a particular behavior of the language is confusing to a lot of people, then I think it's a bit of a problem. So in my opinion, we can say that JavaScript has a bit of a Unicode problem. The way JavaScript handles Unicode is just very surprising, to say the least. And before we get into that, we need to take a closer look at Unicode first, just to make sure that we're all on the same page. So I'm going to explain the absolute minimum that you need to know about Unicode in order to support JavaScript strings correctly, nothing more. So it's easiest to think of Unicode as kind of a database that maps any symbol that you can think of to a unique number for that symbol called the code point, and a unique canonical name for that symbol. And the main advantage of this is that this way it's very easy to refer to a symbol without having to use the symbol itself. You can just refer to the code point, the number, or the name, and everyone will be able to look that up in the Unicode database and know exactly what symbol you're talking about. So for example, there's the Latin capital letter A symbol, that's the canonical name, and the code point for this character is U plus 0041. Now, code points are usually formatted this way. So they're 0 padded up to at least 4 hexadecimal digits. Yes, this is a hex number, not a decimal number. And they usually get the U plus prefix as well. So another example would be the Latin small letter a. This is a completely different character, so it gets its own unique name and its own unique code point as well. I think you start to get the idea now. There's a lot of symbols in Unicode, of course, like the copyright sign, and each one of them gets their own name and code point. There's also a snowman symbol. I'm not sure why that would ever be useful in a text document, but it's there if you want to use it. And while doing my research for this talk, I found out that the Unicode consortium actually added a symbol to the standard specifically for this conference. It's this one. This actually allows you to save one whole character when typing the hashtag for the conference. Now, anyway, there's also a lot of other emoji and other fun characters like the pile of poo. And anyway, if you look at the code point here, we see that the value is 1F4A9. And I told you earlier that code points are usually zero padded up to at least 4 hexadecimal digits, but now we have 5 digits. So you may be wondering what the highest possible code point value is, or how many code points are there in Unicode. Well, Unicode ranges from 0 to 10FFFF. So that's a little over 1.1 million possible symbols. I say possible symbols because not all of these code points have been assigned a symbol yet. Some are not being used today, but in that way, the Unicode standard is future compatible. If next week, for example, a new currency is invented and someone comes up with a symbol for that currency, the Unicode consortium can decide to add this symbol to the Unicode standard. Just pick any of the unused code points and add it in there. Now, to keep things organized, this huge range of 1.1 million code points is divided up into 17 planes that consist of about 65,000 code points each. And the first of these planes is called the BMP, or the Basic Multilingual Plane. And this is probably the most important one of them all because it contains all the most commonly used symbols. In fact, most of the time you don't need any code points outside of this BMP range whenever you're writing a text document in English or German or French or Dutch for that matter. So because the Basic Multilingual Plane contains all the most popular symbols, I like to refer to it as the notorious BMP. Now anyway, just like any other plane, it contains about 65,000 symbols. And that leaves us with 16 other planes consisting of 1 million other code points that live outside of the BMP. And there's a group name for these planes. They are called the supplementary planes or the astral planes. So similarly, when I say astral code point, I just mean a code point that does not belong to the BMP that we talked about. So these astral code points are pretty easy to recognize as well because you need at least 5 hexadecimal digits to represent them. And that's it. That's all you need to know about Unicode. But I can also tell you a little bit about character encodings because Unicode and character encodings, they kind of go hand in hand. You see, character encodings define how strings of text end up getting stored as bytes. And thanks to Unicode, all that a modern character encoding needs to do is just provide that mapping from a code point value to a stream of bits and bytes. And here's a list of encodings that fully support Unicode. This means that they can encode or decode any symbol within that whole range of code points that Unicode has. And this table shows the number of bytes that each encoding requires per code point. Now, one of these encodings is a fixed width encoding. That is UTF-32. As you can see, it uses 4 bytes to encode any code point whatsoever. It doesn't care what code point it is. It will always take up 4 bytes of space. So that's nice and simple, perhaps, but it's not very efficient in terms of storage space. Now, another solution is to use a fixed, well, not a fixed width encoding, but a variable width encoding, like UTF-16, for example. They use 2 bytes to encode any BMP code point, but 4 bytes to encode an ASFL code point. This is slightly better because, once again, the most popular symbols are in the BMP range anyway, so the most popular symbols will take up not as much storage space on your hard drive. Now, whenever you have the choice as to which encoding you should be using, you should really try to go for UTF-8. And there are several reasons for that. For starters, it supports full Unicode, just like all the other ones in this table. But it's also very much optimized for storage. The most commonly used symbols use fewer bytes. It uses 1, 2, 3, or 4 bytes, depending on where in the Unicode range the code point lies. And one of the reasons that are really important and that really contributed to the popularity of UTF-8 is that it is fully backwards compatible with ASCII. So any existing ASCII document is also a valid UTF-8 encoded document. And as you can see, an ASCII code point only takes up a single byte as well, which is very efficient in terms of storage space. And of course, ASCII characters are very popular in text documents all around the world. Now, another very big issue is that other encodings have security issues when they're being used with user-supplied content. And we are all web developers, so we use user-supplied content on our websites all the time. And in that case, it's actually unsafe to use UTF-16, UTF-32, or anything else. Always go with UTF-8 whenever you can. Okay, so with all that in mind, I think we have a basic understanding of Unicode. So let's see how it applies to JavaScript strings now. You may have seen things like this before, where you have, in a string literal, you can have a backslash followed by X, followed by 2 hexadecimal digits. And now that we know about Unicode, it's easy to see what those hexadecimal digits refer to. They refer to a Unicode code point. So this is just another way of representing the string with ABC in capital letters. Now, because we're just limited to 2 hexadecimal digits, there's not a lot of symbols that we can use this for. But it can still be useful in some cases. For example, if you want to use a character with an accent on top of it, and it's hard to type on your keyboard, or you want to keep your source code ASCII safe so that if someone saves the file with an incorrect encoding because they didn't set up their editor correctly, and you don't want the file to break or to be mangled, you can use these escape sequences to represent the string like this, where I use the copyright symbol and an E with an accent on top of it. So this is fairly useful, but still, we only get 2 hexadecimal digits, so we can only use it for very little code points. Luckily, there's another type of escape sequence called the Unicode escape sequence. And these look like this. It starts with a backslash followed by U, followed by 4 hexadecimal digits instead of 2. So this allows us to encode the same characters we did before, but also other code points, like 2661, which happens to be the white heart symbol. So this can be used for a lot more code points. In fact, all the code points in the BMP range that we talked about earlier. However, there's still lots of other code points. If you remember the astral planes, there's like over 1 million code points in there. So how can we escape those symbols? Or another way to phrase the question is, what about our friend the pile of poo and other equally important astral symbols? How can we escape those astral symbols if we can only use 4 hexadecimal digits at a time? Well, the answer is we can do this, kind of, but it's a little bit complicated. In fact, in ECMAScript 6, the newest version of the JavaScript standard, it's really easy because they added a new type of escape sequence called the Unicode code point escape. And it looks like this. It starts with a backslash followed by U, followed by braces. And between the braces, you can use any amount of hexadecimal digits you want. Of course, you only need 6 to be able to represent any code point whatsoever. So by using this type of escape sequence, you can easily escape any Unicode symbol just based on its code point value. However, if you need something that works in older browsers, that works in ECMAScript 5, you're stuck with the unfortunate solution of surrogate pairs. So you cannot use just one escape sequence because you need to represent more data than just those 4 digits. So you just have to use 2. And this is a little bit unfortunate and confusing because the surrogate code points that you see there in the escapes, they don't really look anything like the original code point that we're trying to represent. So these 2 surrogate halves, they form a surrogate pair, and this pair is combined together into a single astral symbol. Now, you may be wondering how we got to these 2 completely different numbers based on the original astral code point. Well, there are formulas that you can use to calculate the surrogate pair based on the original astral code point and the other way around. And here's a JavaScript implementation of those formulas. I don't expect you to remember this exact formula, of course, but apparently you do need to know that this sort of thing exists if you want to be a JavaScript developer that handles strings correctly, which was really surprising to me when I found out about this. So anyway, this whole concept of using a single escape sequence for a BMP symbol, but then requiring 2 separate escape sequences for astral symbols is just really confusing, and it has lots of annoying consequences as well. So let's say, for example, you want to count the number of symbols in a given string in JavaScript. Well, my first thought would be to use the length property of the string. So in these examples, the length property of the string happens to reflect the number of characters in the string. For example, if we take the capital letter A with code point 41, the length of the string is 1. And if we represent that string using escape sequences, well, we count the number of escape sequences, we see that there's only 1 escape there. So this makes sense, right? But what really surprised me is that this is not always the case. The length of the string does not always reflect the number of code points or symbols in the string. Let's try some other characters. There we go. These are different symbols. They even look a little bit similar, but this is actually the mathematical bold capital letter A and B. And so they're different symbols, so they get their own code point value. And in this case, these are actually astral symbols, as you can see. And because of that, JavaScript seems to think the string has a length of 2, even though there's only one symbol there in the string. And the reason for that is because JavaScript exposes each half of the surrogate pair as if it was a separate character, which really isn't the case. And this is very confusing to us because we, as human beings, we generally think in terms of Unicode characters or symbols and not in terms of these surrogate pairs and separate surrogates. It's really confusing. So similarly, if you get a string containing only the pile of poo, the string will have a length of 2 instead of 1. And there's a very obvious joke to be made here for all the Americans out there, but instead I'm going to just show you a real-world example of where this behavior breaks developer expectations and just causes a bug. This is Twitter not too long ago. As you know, they allow 140 characters per tweet, and they don't really care what character you use. If it's an astral character or not, it just counts as one symbol, which is great. But at some point they had a bug in their front end on the JavaScript that displays the counter there. So they would just take the string length and subtract that from 140. And because of that, for every astral symbol you would enter, the counter would decrease in steps of 2 instead of 1, which is not what they wanted in the first place. So because of this bug, it wasn't possible to tweet more than 70 piles of poo at a time. It was truly devastating. Very, very big bug. Anyway, they fixed it. And here's another example. There's a JavaScript library called countable.js, which was quite popular for some time. It takes an input field on your page, counts how many words and paragraphs and characters you enter there, and then displays those numbers elsewhere on the page. And of course, the first thing I did when I saw this demo page for that project was to enter a pile of poo. And, well, it counted it as 2 characters instead of 1. So these are just some examples. I'm not hating on this library at all, because I reported the bug and they fixed it right away. But I'm just pointing out that it's a really honest mistake to make, because the behavior in the JavaScript language is just so surprising. The bottom line is, if you're writing a JavaScript library or you're doing anything at all that involves strings in JavaScript, you have to make it work with all kinds of strings. You can't just limit yourself to the BMP strings, because you never know what kind of symbols your users will be entering. So the easiest way to verify that you're doing this correctly is just to test it like I did. Just throw some piles of poo in there and see what happens. And entering that pile of poo kind of felt like this a little bit, because I could almost predict that something was very likely to go wrong. Yeah. So getting back to our original question, how can it be done? How can we accurately count the number of code points or symbols in a JavaScript string? Well, one way to do this is to use a third-party library that implements those formulas that I showed you earlier. So for example, you could use unicode.ucs2 decode, pass in the string there, and that will return an array of code points in the string. So if you just get the length of the resulting array instead of the length of the string, you will get a more accurate result. Of course, this solution is far from ideal, because now you suddenly introduced a dependency just to be able to count the number of code points in a string. It really shouldn't be that hard. And for that reason, in ECMAScript 6, a new feature was added to the language. Well, these are actually 2 new features. The first one is array.from. You can pass in a string there, and it will turn that string into an array, as you would expect. And internally, this will use the string iterator, which is the second new feature in ECMAScript 6. Because the string iterator is new, it was designed so that it iterates over whole code points rather than these individual surrogate halves for you. So if you run this code, it will give you exactly the same result as the other code, except that this time you don't need any third-party code or libraries at all. Now, another way to do this using ECMAScript 6 is by using the spread operator. You're essentially doing the same thing as in the last slide, but it's a little bit more concise if you like this kind of syntax. Of course, the most efficient solution for this specific problem would be to use a regular expression. You could just replace all those astral symbols with a non-astral symbol and then get the resulting length of the string. That would work as well. Now, I've made a tool that takes any string as input, and then it shows the escape sequences for any special characters within that string. So it's a bit similar to a hex dump, but in this case, the output is always valid JavaScript, which sometimes can be a little bit more useful. So with this tool, it's really easy to see what kind of symbols a string contains exactly, even if the symbols are non-printable or white space or other weird characters like that. So what I've mentioned so far about the astral symbols and the surrogate pairs, you kind of don't have a choice as a JavaScript developer. You have to support all that stuff because you never know when your users will do something like this. But there are some other things that depend on your use case really, but that you may need to take care of as well. And here's an example of that. In this case, JavaScript seems to be telling us that these two strings are different. But visually, they look the same to me. So what is going on there? Well, I tell you what I did. I took those two strings and I copied them into the tool that I just showed you. And this is the output that I got from it. So the first string apparently contains the code point f1, which is the n with the tilde character on top of it, while the second string contains a separate n character followed by the code point 0303, which is a combining tilde. And Unicode has lots of these combining marks, and the way they work is they just get applied to the previous character in the string. So that is why visually these two strings look the same, but if you look at the actual code points that are being used, well, they're actually different, and the length of the strings is different as well. But as a user, we don't really care about this. If we ask a program, what is the length of this string, how many symbols are there in this string, we expect a result of 6 for both strings, right? So how can we get this expected result? Well, ECMAScript 6 has a new feature that helps us with this. It's called Unicode normalization. So to get rid of these lookalike symbols, you just call string.normalize and pass in the normalization form you'd like to use. I'm using NFC here. And that effectively takes care of these lookalike symbols. And after that, of course, we still need to account for astral symbols, just like we did before. But this gives you an even more accurate result than before. Now, is this solution absolutely perfect? Well, once again, this really depends on what you're trying to do exactly. It depends on your use case. For example, if you need to handle crazy stuff like this, where essentially lots of combining marks are being applied to the same string, to the same character over and over again, that is why it looks so weird, well, you have to do a little bit more work. In this case, a lot of combining marks are applied to the same symbol, and visually I would count 9 symbols, including the space. But even our most pedantic function so far would count it as 116, and well, it's easy to see why. So if you need to support stuff like this as well, one solution could be to use a regular expression to kind of remove all those combining marks from the string before further processing it like we did before. That would give an even more accurate result in those cases. Now let's try another example. Let's talk about reversing a string in JavaScript. It sounds fairly simple, right? So how hard can it be? And in fact, this is a very common solution to the problem. You just take the string, you split it up into an array of characters, you reverse that array, and then you glue it back together into a string. And indeed, that seems to work fine. If we reverse ABC, you get CBA, which is exactly what you would expect. If you reverse mañana, where the n with the tilde is a single character, it still reverses the way you would expect it to. But if you try the other mañana, where the n and the tilde are separate code points, now suddenly the tilde gets applied to the A character instead of to the N character. And also if you reverse an astral symbol, like the pile of poo for example, you will no longer get the astral symbol in the resulting string. You will get the same surrogate pair, but the surrogates are now in the wrong order. And this will either not show up or it will show up as some kind of encoding glitch character, which is not what you want in the first place. This is a form of data loss. So even something as seemingly simple as just reversing a string becomes extremely tricky if you need Unicode support in JavaScript strings. Now, luckily for us, a brilliant computer scientist by the name of Missy Elliott came up with a bulletproof algorithm that accounts for all these issues. The algorithm goes, I put my thing down, flip it, and reverse it. And indeed, if you swap the position of any combining marks with the symbol that they belong to, as well as reversing any surrogate pairs before further processing the string like we did before, all these issues are avoided successfully. So thank you, Missy. I actually wrote a JavaScript library called srever that implements Missy's algorithm, so you can use it if you ever do need to reverse a string in JavaScript. Anyway, these were just some examples to make you think about this underlying behavior and about all the issues that you're seeing in the language, but there's lots of other examples that we could talk about. For example, string.from character code allows you to turn a code point, a number, into a string containing the symbol for that code point. It's fairly useful, But the problem with it is that it only works the way it should work for BMP symbols. If you try it with an astral code point, it will give you a result. So it won't throw an error, but it won't be the result that you expect, which I think is even worse than throwing an error. So if you want to use this for an astral code point, you have to do a little bit more work. You have to use those formulas that I talked about before. You have to calculate the surrogate pair for this astral symbol yourself, and then pass those surrogate pairs as individual arguments to the function. So yeah, that is pretty terrible. Another way to solve the problem is to use a third-party library, like Unicode JayZ can do this, for example. You just pass in an array of code points, and it will turn that into a string for you. But once again, this is far from ideal because, again, you're introducing a dependency just to turn a code point into a string. It shouldn't be that hard. And for that exact reason, in ECMAScript 6, there is a new feature called string.fromCodePoint, which is essentially a better version of string.fromCharacterCode. This works for any Unicode code point whatsoever, so you should always use it instead of string.fromCharacterCode from now on. The same thing goes for the character add method on the string prototype. If you use character add to retrieve the first symbol in the string with the pile of poo character, you will only get the first surrogate half instead of the whole pile of poo symbol. And there is no solution for this in ECMAScript 6, but there is a proposal to add something like string.prototype.add, which would automatically deal with full code points and full symbols whenever possible, instead of these surrogate halves. So it is possible to write code that does this in existing JavaScript, but there is no built-in solution for this problem yet. The character code add method has a similar problem. So if you use the code point of the first symbol in the string containing the pile of poo, you won't get the code point for the pile of poo. You will just get the code point for the first half of the surrogate pair, which is probably not what you would expect. But ECMAScript 6 fixes this by adding another method called string.prototype.codePointAdd. And yeah, again, this is like character code add, but it just works the way you would expect it to. So always use this instead from now on. Another example, just to make you think about these issues a little bit more, is iterating over all the symbols in a string. So let's say you want to iterate over all the symbols in a string and do something with each individual character or symbol. Well, you would have to write a lot of boilerplate code in ECMAScript 5 just to deal with those surrogate pairs because you want to combine them into a single character and treat them as one unit. So you would have to write code like this, which is really, I don't expect you to read all this, but it's a lot of code, trust me. You don't want to be writing this. Luckily, in ECMAScript 6, there is a built-in way to solve this problem now. You can use the new for-of construct to loop over a string, and that will once again use the string iterator that we talked about before. The string iterator deals with whole code points automatically, so this way you won't have to deal with surrogate halves anymore. It's much easier. Now, I could go on about this. There's more examples of string methods that are kind of broken in this way, like things that take a position argument, like substring or slice. They're affected by this as well, because the position is not the position of the symbol or the code point, but it accounts for the surrogate halves and pairs as well, which is kind of confusing. And really, anything that involves strings at all is affected by this. And all of that is really unfortunate. But as Tupac would say, that's just the way it is. Some things will never change. And that is also the reason why ECMAScript 6 added so many new methods to the language rather than just updating or fixing the existing ones. That would be impossible to do because there's a lot of code out there on the web and also in Node.js that would suddenly start breaking if the behavior of those functions were to change. So even though the behavior is broken, JavaScript developers have come to rely on the broken behavior. So rather than fixing the problem, we can only add new functionality to work around the issues, unfortunately. So I've talked about strings so far, but one thing that goes hand in hand with strings is regular expressions. So let's talk about that for a second. The dot operator in regular expressions only matches a single character, right? But because JavaScript exposes these surrogate halves as if they were separate characters, the dot operator won't ever match an actual symbol. So it doesn't really do what I would have expected it to do. If I write a regular expression foo.bar, I would expect it to match the string foo pile of poo bar, for example, but in JavaScript it doesn't. So let's think about that for a second. If we can't use the dot operator, what can we use to match any Unicode symbol or any Unicode code point whatsoever? What would that regular expression look like? Well, we cannot use the dot operator, as we've just demonstrated. It wouldn't match astral symbols. It also wouldn't match line breaks. We can solve the line break problem by doing something like this, where you match all the white space characters and then also match all the non-white space characters. So you would essentially match all the characters. But again, because JavaScript doesn't consider astral symbols to be one character, but rather two, it still wouldn't match our astral symbol. So any ideas on what the regular expression should look like to match any Unicode code point at all in JavaScript? Yeah, I wouldn't know either, but apparently it looks like this, which is kind of crazy, right? I mean, this is not the kind of regular expression I would enjoy typing out by hand, let alone maintaining it. So I didn't write it by hand. I actually used a JavaScript library called regenerate to generate this regular expression for me. And here's how I did that. So I just created a new regenerate instance, added the whole range of Unicode code points to the set, and then called toString on it. And that returns a regular expression pattern that I can use as part of a regular expression. The reason it returns a string is because regenerate is supposed to be used as part of a build tool, so it can write the string to a JavaScript file as part of your regular expression, for example. It has some other features as well, like, for example, you can create a new set, then add all the Unicode code points in existence to the set. Then you can remove a range of characters based on their string values, in this case from uppercase A to lowercase z. And then also remove the pile of poo and then turn that into a regular expression. And that would only match the characters that you specified. And again, there would be no way for me to actually predict what this regular expression would look like, and it would take me a long time to write a regular expression that does this exactly by hand. But with regenerate, it's just running a script and it generates the regular expression for me. So imagine having to remove yet another character from the match set for this regular expression if all you could edit was the regular expression itself. It would probably take a long time, right? I mean, I know it would take me a long time, but if you have those 5 lines of code right above it, it's fairly simple to just add another line to it or tweak that script a little bit. So my advice is, if you ever need complex regular expressions that match Unicode correctly, use a build tool like regenerate, for example, to do it for you. Don't go crazy and write it out by hand. It's insane if you're doing this. Another example is, let's say you want to match all the symbols in the Greek script, for example. Well, the good news is Unicode has built-in data tables that contains all this information. So it has a listing of all the symbols in the Greek script, for example. And I have created a tool that converts all these data files into JavaScript arrays, so you can just require them in Node.js and use them right away. So here I'm just requiring a list of symbols in the Greek script according to Unicode version 6.3.0, and then feeding that array into regenerate, turning it into a regular expression, and apparently that regular expression looks like this. Once again, not something anyone would enjoy writing out by hand or maintaining. Now, the problem with this regular expression here is that it's already out of date. I've been using the data for Unicode version 6.3 in this case, but the latest version of Unicode is version 8. And in fact, in a couple of weeks, version 9 will be released. So let's say you need to update this regular expression. If you only had that regular expression, it would probably take a lot of time to update it based on the latest standard. But now that we have those 4 lines of code, which is essentially our build script, it's very easy to update this to the latest version. You just update the Unicode version number in your code, run the script again, and just like that, a new regular expression comes out that is perfectly up to date. So once again, these regular expressions are crazy. Don't write them by hand. Use a tool that does it for you. And save the code that you use to generate the regular expression as a build script. Now, getting back to our problem of matching any astral symbols as well and making the dot operator match astral symbols as well, there is a solution for this in ECMAScript 6. There is a new flag for regular expressions called the U flag, which stands for Unicode, and this enables the behavior that you would expect from the dot operator in the first place. So with this flag, it would match the pile of poo and other astral symbols. Now, another example is character classes in regular expressions. For example, if you do something like this, A-C in between the brackets there, you create a character class with a range that matches A, B, and C. This is how you expect it to work. And similarly, you might expect this regular expression to match the pile of poo, the flexed biceps, and the dizzy symbol, because those are consecutive symbols in the Unicode standard. It's essentially the same example as this one, only with different symbols. But unfortunately, it doesn't quite work that way in JavaScript. In fact, this very first line of code, the regular expression itself, would already throw an error. It would say, the syntax error, there's a syntax error, the regular expression is invalid because the range is out of order in the character class. So what is going on there? Well, as far as JavaScript is concerned, this is what that regular expression looks like. Because each astral symbol consists of a pair of surrogates. So it looks at it like this, and now it doesn't try to create a range between the pile of poo and the dizzy symbol like you intended to do, but it tries to create this range instead, between one of the surrogates and another one of the surrogates, which is not the correct range in the first place, and it also throws an error because the first number is greater than the second one. So yeah, this doesn't work at all. Of course, in ECMAScript 6, you can fix it just by using the U flag that we were using before. That just magically makes this regular expression work the way you would expect it to work, which I think is great. However, if you're stuck with an older environment, because not all browsers support this feature yet, well, you're back to using a tool like Regenerate to generate a regular expression for you at build time. So here's how we can do that. You can just create a new set, add the range of characters you want to match, turn it into a pattern, and apparently that regular expression looks like this. So because it's really bothersome to have to write a build script like this for every regular expression you want to write if you want to support full Unicode, I set out to create a transpiler, so a piece of code that takes your existing ECMAScript 6 regular expressions with the U flag and translates them into an equivalent regular expression without the U flag that works in browsers of today and even in IE6 if you want to use IE6. So here's the demo of that. The project is called regexpoo because the flag name is U. And it's being used in Google's Tracer transpiler and also in Babel. So the two most popular transpilers have regexpoo built in, and they use it for their transpilation of regular expressions. So the good news is you can already start using code like this. Well, let's just zoom in there a little bit. So you can already start using the U flag in your code because you already have a build process for your JavaScript files anyway, right? And if you're using a transpiler like Babel or Tracer, you just write code like this, and it will turn it into an ECMAScript 5 equivalent piece of code that works in older browsers as well. I think it's pretty neat, but there are still some issues that aren't resolved in ECMAScript 6. For example, if you go back to our Greek script symbols, there's still no way to do this in the language natively. You still have to use a build script that generates this huge regular expression for you and then use that as part of your source files. But everyone agrees that it would be really nice to have something like this in a future version of JavaScript, where you could directly target the Unicode data and Unicode properties like this. So you could use \p, and then in between braces, you could specify the Unicode property and value that you want to target. So in this case, this is what that same regular expression that was huge before, it could be reduced into something like this if this feature were to be supported someday. And there's a lot of more stuff that you can do. It's not just for scripts and Greek symbols. You can target alchemical symbols, for example, and then you can test it. If you try the alchemical symbol for fire, which is the triangle you see there, you would see that it matches this regular expression. Or you can match any number whatsoever in Unicode. So there's not just the numbers from 0 to 9 that we are using. There's a lot of numbers in other scripts as well. And there's things like fractions of 3/4, for example. Those are also numbers. And just by using this property, you will be sure to match all of those as well, not just from 0 to 9. For example, if you want to match all the mathematical symbols in the Unicode standard, you could use \p math, and that would match things like the Euler's constant, for example. And well, everyone agrees that this kind of feature would be really amazing, and that this would be a nice addition to the regular expression grammar in JavaScript. But the problem is that no one wants to write the specification for it, and so far no one has done this, and that is the main problem. I'm not saying that I will be writing the specification, but I'm currently working on a patch to add support for these special Unicode property escapes to my existing transpiler. And in fact, I've already got the code working. I just need to clean it up a little bit and release it so that people can start experimenting with it. And the reason I worked on this is to get a better feel of the edge cases surrounding this feature and to get a better idea of what a good specification for this feature would look like. So I think we can all agree that JavaScript has a Unicode problem. There's been a lot of solutions so far, but we're not quite there yet. But rather than complain about this like JayZ did, I think we should be doing more of this instead. Yeah, we should just deal with it and work around these issues, because really it's not that hard. I gave you a lot of workarounds in this presentation. I think all we can do is just add some piles of poo to our unit tests, and that will lead to lots of bugs being discovered, and that's a good first step towards getting these bugs resolved, of course. So if every one of us would just submit a quick pull request today to a JavaScript project that they're using that deals with strings in some way, and just add a single pile of poo to the unit tests, I'm sure that collectively we would be able to discover lots of bugs, and that would be the first step to getting them resolved. So I think the problem is not that developers don't want to fix all these issues. I think the problem is a lot of people just don't know about them, because really the behavior is just so surprising and unexpected. So my advice would be to go forward and spread piles of poo, I guess. Thanks for listening. Cheers. I think we have some time for questions, if anyone's up for it. Too early in the morning? Okay, let's get some. Okay, there's a question.
Possibly, in that last slide, you had property values and the categories.
Mm-hmm.
So yeah, when you go about it, why do you need property value there? That was something you proposed. Why not just a keyword type?
So you mean \p number instead of \p? Because there's lots of different types of properties, and some of them have the same names, so there would be things that overlap. And in fact, this is not something that I made up, this kind of syntax. Perl already has something like this, and there is a document in the Unicode standard that defines how an implementation, well, it doesn't define the syntax, but it defines kind of the specification of how this sort of feature could work, and it lists this as well. And for the last example, we're just using math, because that is a binary property in Unicode. It just has a true or false value, so there is no duplicates there. You can use it for that as well. Also, for the general category example, you can omit the general category equals part as well, because there's no duplicates there. But for everything else, like blocks and scripts, and there's other stuff as well, like BD properties, you would have to specify the property equals the value name as well. Any other questions? Okay, let's go get some coffee then. Cheers.